Welcome back to the deep dive. So you handed us, well, it's a single, very dense research paper.
It is, yeah.
And our mission today is to really get into the weeds on the K-essence scalar field model of dark energy.
We're tackling the big one here. The greatest puzzle in physics, really. Late time cosmic acceleration.
That's it. We know the universe isn't just expanding, it's flooring the gas pedal.
And K-essence offers this pretty radical explanation, one that ties the whole cosmos back to the tiniest mechanics of string theory.
Okay, let's unpack this. We have to start with the problem, right? The reason K-essence even exists.
Right.
We look out there, and the universe is inflating faster now than it was billions of years ago. I mean, that discovery was a huge shock.
It was. It demanded some kind of repulsive gravity, something we just, generically call dark energy.
And we wouldn't even be having this deep dive if the evidence wasn't, well, if it wasn't completely rock solid.
Absolutely not. The source material is very clear on this. This isn't some shaky idea. It's a triply confirmed phenomenon. You have 3 totally independent lines of observation, which is, that's the gold standard in science.
So let's tick through them. First up, the source cites baryon acoustic oscillations. BAOs.
Right.
For anyone who hasn't deep dived into this lately, what are we actually looking at with BAOs?
Okay, so think of the very early universe. It was just this incredibly hot, dense soup of plasma.
Before any stars or galaxies.
Before. And you had sound waves, or really pressure waves, traveling through this plasma.
Okay.
But then the universe cooled down enough for the first atoms to form. And at that exact moment, the waves basically, they froze in place.
Like a photograph was taken.
Exactly. It's a snapshot. And the distance those waves traveled before they froze gives us a standard length, a kind of cosmic ruler.
And how big is this ruler?
It's about 500 million light years across. And because we know its true size, we can look for that pattern in how galaxies are distributed today.
So if we know the real size, and we measure the apparent size way out in the universe,
you can map the expansion history of the universe with incredible precision. And that map tells us things were slowing down for the first half, and then about 5 or 6 billion years ago started speeding up.
the acceleration.
The acceleration. BAOs nail it down.
Okay, line of evidence number 2. The cosmic microwave background. The CMB.
The afterglow of the Big Bang itself.
Now, how does something from just 380,000 years after the Big Bang tell us about acceleration happening now?
Well, the CMB gives us the universe's total energy budget, the little temperature spots, the anisotropies. Their size tells us something crucial.
Which is?
That the universe is geometrically flat.
Meaning all this stuff and energy in it has to add up to the critical density?
Precisely. But when we actually add up all the normal matter, all the dark matter, we only get to about 30% of that number.
So there's 70% missing.
70% is just gone. And that missing piece has to be the dark energy. The CMB demands its existence to make the numbers work.
And the third piece of evidence. The source calls it the power spectrum of matter distributions.
That's the large-scale structure. The cosmic web, the filaments and voids of galaxy clusters.
Right.
The way that structure grew over time is very sensitive to what's in the universe. If it were just matter, everything would have clumped together much, much more aggressively.
So the growth we see is a little bit stunted.
Stunted is a perfect word for it. The repulsive force of dark energy doesn't just push galaxies apart. It slightly suppresses the formation of these huge structures.
And that suppressed growth rate perfectly matches a universe with about 70% dark energy.
It's a perfect fit. So you have 3 different measuring sticks, BAOs, the CMB, galaxy clustering, all pointing to the exact same conclusion. You have to take that seriously.
The evidence is overwhelming. So what's the simplest explanation physics came up with, and why isn't it good enough?
The simplest solution is the cosmological constant, lambda. Einstein's biggest blunder that turned out to be maybe not a blunder.
What is that mathematically?
It's just energy that's intrinsic to the vacuum of space itself. Its density never changes, even as space expands.
So as matter and radiation dilute away, this vacuum energy just stays constant and eventually takes over.
Exactly. And it corresponds to an equation of state omega of exactly -1.
Okay, that sounds really simple. It sounds great.
Yeah.
Why are we even talking about something as complicated as K-essence if omega equals -1 works?
2 big reasons. The first is theoretical, and it's a catastrophe. Quantum field theory predicts a value for this vacuum energy that's owed us. It's about 10 to the power of 120 times larger than what we observe.
In 120 orders of magnitude.
It's the worst theoretical prediction in the history of science. It's a huge problem.
Okay, so that's problem one. What's the other?
The other is observational. Our best data from supernovas and other probes, it hints that omega might not be exactly -1.
It could be changing over time.
It could be evolving. So if we can build a model that naturally predicts a dynamic evolving omega, that's a huge step forward.
And that's the whole mission for K-essence.
That's the mission. K-essence is part of this whole family of ideas called scalar field models. You've got quintessence, tachyon models, all sorts of things.
So what gives K-essence the edge?
Its origin story. It's not just a mathematical gadget we invented to fit the data. Its core structure, its Lagrangian, is directly motivated by string theory.
It comes from a fundamental theory of quantum gravity.
Exactly. It suggests it might be a real physical thing, not just a placeholder we're using until we find the real answer.
That's a critical distinction. It's bottom-up physics, not a top-down fit.
Precisely.
Okay, so let's get into it. How do we actually define this model?
All right, so it all starts with the action, S. And the action for K-essence is defined by its Lagrangian density, which we call P of phi and X.
A is the scalar field itself, the thing doing the work. But this other term, X, this is the heart of the model, isn't it?
It is absolutely the heart of it. X is the kinetic term. It basically measures how fast the field is changing or moving across space-time.
So if the field is just sitting still, X is small. If it's rolling fast, X is large.
That's it. Now, in a normal standard field theory, the Lagrangian is just kinetic energy minus potential energy. It would just be proportional to X minus V of phi.
The canonical form.
The canonical form. But K-essence is non-canonical, and that changes everything.
What does that mean, non-canonical?
It means the pressure, P, isn't just a simple linear function of X. It's some complex nonlinear function of X. The source paper uses a separable form, P equals minus V of phi times F of X.
So the innovation is that the pressure isn't just about how fast the field is moving, but some more complicated function of its speed.
Yes, the field's own motion interacts with itself in a way. It's self-regulating. This lets the field generate this incredibly strong negative pressure, this repulsive gravity, even if its potential energy is very flat.
Ah, so it decouples the need for acceleration from the specific shape of the potential.
That's the power of the model. It adds this whole new degree of freedom. It's why K-essence models can have these tracking solutions where their energy density naturally follows the background matter for a while before taking over.
Which is very hard to do with standard models without a lot of fine-tuning.
A lot of fine-tuning there.
And there's a really interesting piece of history here, right? This wasn't even invented for dark energy.
No, not at all. It was first developed to explain inflation, the universe's first tiny fraction of a second of super rapid expansion.
So it was called K-inflation.
K-inflation, yeah. Developed by Armendariz Picon and his collaborators, they showed that this non-canonical kinetic term, this weird function of X, could drive that initial burst of expansion all by itself.
Without needing the slow-rolling potential that standard inflation models use.
Right. The kinetic energy itself was the engine, so once they showed the mechanism worked for the beginning of the universe.
It was a pretty small leap to try it for the end of the universe.
It was. Chiba and others repurposed the exact same idea to model dark energy, and it worked beautifully.
That's amazing. A single physical idea that could solve two completely different acceleration problems at opposite ends of cosmic time.
It's just a real unity in the physics, doesn't it? If this field is real, its influence could span the entire history of the cosmos.
Okay, so we've established the structure. The non-canonical term X is the key. But where did this bizarre Lagrangian even come from? Which brings us to the string theory connection.
And this is where it gets really profound. We move from, a mathematical curiosity to fundamental physics.
Because most of these models are just made up to fit the data.
Exactly, they're phenomenological. K-essence is compelling because this exact non-canonical structure just falls out of the low energy limit of string theory. It's an emergent property.
So just remind everyone, string theory lives in 10 or 11 dimensions.
Right, and to connect it to our world, you have to compactify or reduce those extra dimensions down to the 4 we see.
And when you do that,
you generate an effective theory in 4 dimensions. And that theory always includes a specific kind of scalar field called the dilaton field.
the dilaton, what's its physical job in the theory?
The dilaton field is fundamental. It controls the strength of the interactions between the strings. The string coupling constant g squared is just e to the power of phi, the dilaton field.
So if the dilaton changes, the fundamental forces of nature change strength.
Precisely. So it has to be there and it has to be dynamic. It's a natural candidate for the field driving cosmic expansion.
And the source paper highlights that the action you get from this process is, well, it's very complicated.
It is, because strings aren't point particles, they're extended objects. So the action includes all these correction terms based on the string length.
The alpha prime corrections.
The alpha prime corrections. And what that means is your action doesn't just have a simple kinetic term squared. It has terms proportional to the kinetic term to the power of 4 and higher.
So string theory itself is telling you that the Lagrangian has to be nonlinear. It has to be non-canonical.
That's the crucial insight. These higher power terms, which become the nonlinear f of x in the k-essence model, they are an unavoidable consequence of the theory. They aren't just tack on.
Okay, so we have this complex action, what's called the string frame, but we need to analyze it in the context of general relativity. How do we get there?
You have to perform a crucial mathematical step. It's called a conformal transformation.
Which sounds intimidating.
It does, but all it really is, it's like a mathematical cleanup. You're just rescaling the metric, the thing that measures distances, by a function of the dilaton field.
And why do you do that? What's the point?
In the string frame, gravity itself is coupled to the dilaton field, which makes it look non-standard. The transformation basically untangles them.
So you end up with standard general relativity on one side, and all the weird, exotic new physics is now contained in the matter sector, in the scalar field.
Exactly where we want it to be to describe dark energy. You put all the new physics into the field, and you leave gravity looking like the Einstein gravity we know and love.
And what's the result when you do this transformation on the string action?
The effective Lagrangian you generate has a very specific form. It looks like P of phi, x equals k of phi times x, plus L of phi times x squared, plus higher order terms.
That's it. That's the k-essence Lagrangian. It has the standard linear term in x, but it also has that crucial non-canonical x squared term.
It confirms the link. The source is explicit. This form proves that the string theory action can be represented as a k-essence scalar field.
So the model isn't just a choice. It's a prediction from our most fundamental theory of quantum gravity.
That's what gives it such a powerful motivation. It's a direct realization of a deeper theory.
Incredible. Okay, now let's see what this structure actually predicts.
Yeah.
Section 3, the equation of state. This is all about omega.
Right. Omega equals pressure over density. This is the cosmological fingerprint of the field. Remember, for acceleration, you need omega to be less than minus 1/3.
The source paper uses a simplified but representative form to show the physics. It sets that nonlinear function f of x to be x minus x squared.
It's a great example because it has the nonlinearity, but it's simple enough to work through. From that, we can derive the energy density, Rocho, and the pressure.
The pressure is just the Lagrangian itself, right?
All right, so P is minus V of phi times the quantity x minus x squared.
Okay, and then the density, ρ, is given by a slightly more complicated formula involving the pressure and its derivative with respect to x.
That's right. So we calculate that derivative, which is minus V of phi times 1 minus 2x. Then we plug everything into the density equation.
So ρ equals minus p plus 2x times the derivative of p.
And when you substitute everything in and do the algebra, you find that the density, okra, is V of phi times the quantity 3x squared minus x.
So both the pressure and the density are these nonlinear functions of the kinetic term, x.
Correct. And now for the main event. We calculate the equation of state, omega, by dividing pressure by density.
So we take minus v of phi times x minus x squared and divide it by v of phi times 3x squared minus x.
And the first thing you notice?
The potential, v of phi, it just cancels out.
It's gone. Completely.
Wait, so the shape of the potential doesn't matter for the equation of state at all?
Not for the equation of state, no. That's the first huge insight. The gravitational behavior of the field is determined entirely by its motion, by x.
Wow. Okay, so what are we left with?
You're left with omega equals 1 minus x divided by 1 minus 3x.
That simple ratio.
That simple ratio contains all the cosmological power of this model.
Okay, let's analyze this. What if we want to mimic a cosmological constant, where omega is exactly minus 1?
You just solve the equation, and you find it's true if and only if x equals 1/2.
So K-essence can perfectly reproduce the standard dark energy model. It contains it as a special case.
It does. But the really important question is, when does it drive acceleration? When is omega less than -1/3?
And what does the math say?
The math says that this condition is met whenever x is less than 2/3.
So as long as the field is rolling slowly enough, with its kinetic energy below that threshold of 2/3, you are guaranteed to get accelerated expansion.
Guaranteed. And that's the profound advantage. In a normal quintessence model, you need the potential energy to be huge and the kinetic energy to be tiny. Here, the non-canonical structure itself generates the negative pressure.
It's an intrinsic mechanism. It's not about fine-tuning a potential.
The dynamics themselves give you acceleration.
And of course, all of this has to live inside the standard Friedmann equations, which govern the whole universe's expansion.
Yes, we're assuming a flat universe, which is what the CMB data tells us. K-essence has to work alongside matter and radiation to produce the universe we see.
Okay, so the theory is beautiful. It's motivated by string theory. It has a mechanism for acceleration. But does it actually match the data? Let's move to observational feasibility.
Right, before we get to the late-time universe, the paper touches on the original K-inflation dynamics again.
Back at the beginning of time.
Right. And it points out this interesting scaling relation that the model preserves. When the potential v is constant, you find that x times the derivative of f squared scales as a way to the -6.
A to the -6, that's diluting incredibly fast.
Right.
Matter is an A to the -3, radiation is A to the -4.
Exactly. It shows that this purely kinetic-driven phase, the K-inflation, would have been very intense but also very short-lived. It does its job and then gets out of the way, which is what you want.
That's a good consistency check. But now for the real test. Supernova data.
Type IS supernovae are standard candles for mapping the recent history of the universe.
They give us a direct measurement of the expansion rate, h, and the scale factor, a, over time.
And the game is to take that real-world data and plug it into the complex dynamical equations for the K-essence field.
And you try to solve for the field's evolution for phi of t. If the answer you get is something crazy or unstable, the model is wrong.
It's a brutal test, but the result, as the source shows, is incredibly compelling. When you fit the equations to the data, the whole system simplifies.
In what way?
The required evolution for the field, phi of t, turns out to be this beautifully simple mathematical form.
The paper says it's like an exponential decay, or a simple low-order polynomial.
Exactly. And the fact that the complex theory, when constrained by reality, collapses into such a clean, stable solution, that's a huge victory for the model.
Why is that a victory?
Because it could have been anything. It could have required the field to behave in some physically impossible way. Instead, it shows a smooth, well-behaved evolution that perfectly tracks the observed expansion. It's feasible.
So K-essence passes the theoretical test, and it passes the observational test.
It moves from a curious idea to a front-running, observationally supported candidate for dark energy.
Okay, this is where it gets really interesting for me. We've talked about the past. Let's talk about the future. Section 5, K-essence in a mixed universe and stability analysis.
Right, because in the real universe, K-essence isn't alone. It's coexisting with normal matter and radiation.
Which we can model as a simple barotropic perfect fluid with a constant equation of state, omega m.
Right. 0 for matter, 1/3 for radiation. And now you have this highly complex, coupled system. The K-essence density and the matter density are both influencing the expansion rate, which in turn influences how they both evolve.
It's a feedback loop.
It is. And when you write down the full set of equations, they become horrendously nonlinear and difficult to solve.
The paper gives an example that results in an equation with the field velocity raised to the 6th power.
Yes, it's a mess. And a system that complex is likely to have multiple possible fates, multiple stable endpoints, or fixed points.
And the standard way to figure out what will happen is linear stability analysis.
You find the points where the system could settle down, and then you give it a little mathematical nudge to see if it comes back to the point or runs away.
You check the eigenvalues of the system. If they're negative, it's stable.
If they're negative, it's stable. If they're positive, it's unstable. That's the standard playbook in dynamics.
But the source material flags a huge problem here. It says the standard analysis fails.
It fails.
How can it fail? It's the standard tool.
It fails because of the incredibly subtle, nonlinear structure of the K-essence field itself. The analysis depends on a key mathematical idea. the Poincaré-Lyapunov theorem.
Okay.
And that theorem only works if your fixed point is what's called hyperbolic, which basically means the linear approximation gives you a clear answer, either stable or unstable.
And k-essence isn't hyperbolic.
No. When you analyze the system, you find that the fixed points are nonlinear. The eigenvalues have 0 real parts.
Meaning the linear analysis is inconclusive. It tells you nothing.
It tells you nothing. The higher order nonlinear terms that you usually ignore, they become the most important part of the story. The standard simplification breaks down.
So the very thing that makes k-essence so interesting, its string theory origin, its nonlinearity, also makes its ultimate fate impossible to determine with our standard mathematical tool.
Exactly. The interaction between this field and normal matter is far more subtle than we're used to. And because the simple method fails, you have to bring out the big guns.
Which, according to the source, is a technique called Hopf bifurcation.
Hopf bifurcation analysis.
Okay, break that down. What's a bifurcation?
A bifurcation is a tipping point. It's a point where a tiny change in one of the system's parameters causes a sudden, dramatic change in its long-term behavior.
And Hopf bifurcation is a specific type of this.
It is. It's what happens when a stable point suddenly becomes unstable, and in its place, a stable orbit or a limit cycle appears.
An orbit? You mean the universe wouldn't settle down into a static state, but would oscillate?
Precisely. Instead of just settling into a state of eternal, constant acceleration, the system could stabilize onto a cycle. The energy densities and pressures could oscillate over cosmic timescales.
That is a fundamentally different vision of the universe's future.
It is. The fact that you even need to use a tool like Hopf bifurcation shows how rich and complex the dynamics of this model are. It suggests the universe's fate might be inherently cyclical, not static.
This is a phenomenal journey. We started with a simple question about cosmic acceleration, and we've ended up deep in nonlinear dynamics and the potential for an oscillating universe.
We really bridged the gap from fundamental theory to observational cosmology and then into the mathematics of the deep future.
Let's distill the key takeaways for everyone listening. The first one has to be the origin story.
Absolutely. Takeaway number 1. K-essence is so compelling because its non-canonical Lagrangian is not just an invention. It is a direct prediction of string theory.
It's grounded in fundamental physics, which gives it a huge advantage over other models.
Takeaway number 2 is the elegance of the mechanism itself.
The equation of state, omega equals 1 minus x over 1 minus 3x.
It depends only on the kinetic term. It gives you an intrinsic dynamic engine for acceleration. As long as x is less than 2/3, the universe accelerates. It's that simple.
And the third takeaway, it actually works in the real world.
It does. The model's ability to fit the supernova data and for the field to have a simple, stable evolution confirms its observational feasibility. It's a robust, serious candidate.
Which brings us to our final thought. Back to that complexity, that need for Hopf bifurcation.
Right. So if the true dynamics of our universe are so complex that our simplest stability tools break down,
It means the future might be a lot weirder than we think.
it poses a really profound question. What new, potentially cyclical or even chaotic behaviors might these nonlinear dynamics unlock in the far future? If the universe stabilizes onto an oscillating limit cycle instead of a fixed point, could we be in for an endless series of cosmic epochs, with acceleration followed by deceleration over and over again?
A universe that never truly settles down. A fantastic thought to end on.
There's always more to explore.
Thank you for navigating this deep dive with us. We'll see you next time.